Let me introduce my three colleagues. Starting at the far end of the table, we have Charles Pooh, followed by Roger Germanson and Andy Ross. Well, Charles, let's start with you with one of the biggest features inside Mathematica 9, social network analysis. Tell us about it.
Thank you, Zach. I'm going to give an overview of social network analysis in Mathematica 9. So as you all know, networks are all around us, especially social network, which is made of, a set of actors we tie between them. By actors, I mean, individual like you and me, which are connected to friendship, or organizations which are connected to, business transaction or such a thing. So finding important people in those networks, like in your professional network, or finding communities or cliques in your Facebook network are example of type of analysis you can do on social networks. So built on the strong Mathematica graph capability, Mathematica 9 allows us to actually model and analyze networks. So in the next couple of slides, I will try to give you an overview and the general idea behind the design we have for social network, as well as all the power and feature we actually offer to you to play with. So first of all, I will show you how to access data. So I will talk about social network data, Facebook connectivity, and other type of connectivity. And then next, I will look at the analysis side and first talk about centrality, prestige, and role, which is at the actor levels. And next, at the group level, I will talk about community detection, so how to find out community and find cliques and other features. And then I will end up with looking at assortativity and clustering, which is at the network level. There is plenty more feature, actually, I will not cover here, but I will at the end kind of point you to the resources which are available in Mathematica and through our website. So let's first start of how to build a network, how to access data in Mathematica, your network. So if you're coming from a theoretical background, first of all, we like to actually build network and simulate networks. So we kind of offer you different type of network, scale-free network, small word network, which are coming from the Barabasi-Albert model, and the other one, the Wastrogas models. These are already available in version 8. And what we did in version 9 is that we enhanced those graphs in terms of performance and actually scale, how they scale in terms of memory and size. So also what we did is that we extended our collection of empirical networks. And we included some standard networks, such as the Southern Women Club network, which is kind of one of the first data sets collected by David and colleagues in the 1930s for the first, at the early stage of network analysis, social network analysis. So here you can just evaluate it in Mathematica and you get the network, which is actually a two-modal network, where you have the 14 women there, and then you have the corresponding event, 8 event on the right-hand side. So the other side also we have in Mathematica is that you can import your data. When you do your research, you collect data. You can collect it in Excel, or you can have it in a, in CSV file, tabulated data. You can import it in Mathematica already. But what we did is that we added actually specific file format or data format for graphs, so you can import them in Mathematica quite easily. So here you can, import a GraphML file, and also you can actually export it to other data formats like project here. If your colleague, have project and want to play with your data set, you can actually just do your work in Mathematica and export it and distribute it to your user. So one of the new features actually in version 9 in terms of social network access to the data is that we introduce a new parklet we call social media data, which allow you to actually access the different social media we have around there. So Facebook, LinkedIn, Twitter, Google+ are the first few we introduced in this version. And this is a parklet, so it's load on demand, and maybe in the next couple of months or so, you will see more social media supported. So I will just try to give you a brief demonstration of how it works. my colleague Andy was nice enough to let me use his account. He have a much nicer social media network. So first of all, if you do social media Facebook property, you will get the list of property we actually provide you. So it's an interface to your data directly. You can export your image as well as any other posts you actually make on Facebook. Or you can directly look at the list of your friends, which is an extensive list here from Andy. You get it in directly, and then just use Mathematica to get the list of the friend. And if you come directly to the social network side, you can actually look at your friend networks. And there we have Andy friend network. I will just make it slightly larger. So this is a pretty nice network. We kind of try to actually give more information visually, except besides just the layout, kind of provide you, more information by just looking at the networks. So for example, this network have different color, which probably Andy can tell us more. There are probably different communities he can recognize here. Do you recognize, for example, this community in orange?
Read me a name because I am having trouble seeing your screen.
Oh, that's Campbell, Clint Campbell.
Oh, right. So I was actually a teacher at one point, and that's a group of students that I used to have.
I see.
So each of these clusters, I've looked at this several times, they sort of represent critical points in my life. So the orange area is people that I taught with or worked with when I was a teacher. And the sort of circle above in red are people that I went to high school with.
Okay.
Over there to the left would be, let's see. Oh, yeah, so this would be like my elementary school years. And the big red dot in the middle is my wife, who is kind of who I'm connected to everyone through.
Okay. Oh, thank you. So as you see, we actually kind of provide more additional information, not just the layout in the output. And this graph is, this network is actually an object in Mathematica. You can directly just, operate on it. And then, it behaves like any other object in Mathematica, and it just works. Okay. So the other social media data we actually have, our social site we actually introduce here is actually Twitter's. So Twitter is also identical to Facebook. We try to make the interface uniform and standard to our data packlet. So feel free to go and look at the collection of data we have for Twitters and look at your friend network or follower networks. Okay, before I actually look at the analysis now, I will just kind of point out what I just said is that the network in Mathematica actually display like a graphic, and it actually have the whole full power of our graphic. That means automation and algorithmic aesthetic methods, as well as information visualization. You can highlight nodes or actors or part of the group and do labeling. So this is just a basic example. So this was the original Andy networks. So I can take it and then just do a community plot, which is a new function in Mathematica, which actually compute those communities explicitly now and put a lasso around it. And then you can actually see those communities we had earlier up there with different color. But now the layout is also modified. So that's actually more information now based on layout. OK. So this is kind of the aspect of how to get the data. So we have a lot of functionality there, import and direct access to social media. So now let's look at the analysis, the analytic part. So as I say, we have roughly 3 levels. The actor level where you study people, the group level by group, and then the network level. So at the level of the actor, so essentially the measure we provide are centrality and prestige measure. And you can use them to actually analyze your network and detect role for people. So what we provide you is about 8 centrality measures. Several of them are already in version 9, version 8. We actually enhance them in version 9. We make them more faster and more efficient, actually, in terms of memory as well as scale too. And we introduce new ones as status centrality and radial centrality, radiality centralities. And here I will actually show you one nice example, which is about the Medici family. As you all know, the Medici family, didn't have, a great amount of money, and a lot of seats in the legislature in the 14 as if Florentine families at the time. But always in history, we know that they are kind of important. So one tool to actually figure out why in history the Medici family was actually so important is to look at the marriage network and apply social analysis to it. So when you actually do that, here we actually provide already the data set. So when you do that and then actually look at the betweenness centrality, which kind of give you or kind of rank people or actors in the network based on the way they connect. So here it actually shows you that the Medici come first, are ranked first in terms of betweenness centrality. That means if there is an information which has to be transmitted between those families, based on their marriage, they actually have access to those type of information which allow them to actually good in breaking deals and doing other things. So you can also look, for example, at the closeness centrality related to them. So how close are they to other families? And you can see also that the Medici is coming first. So that means also they are more close to other families in 14th century Florentine families. So this is a nice way to actually apply social network to analyze and understand why something happened in history and how they were, some families have certain positions. So this is the level of the actor. So now let's look at the group level. So at the group level, we provided a collection of cohesive groups as well as community detections. So by one of the example of those groups are cliques, a subgroup of people which are all connected together. So you can use the function find clique in Mathematica to get it. It's quite efficient and really fast. In this example below, we take, for example, the 2010 National Hockey League game. And there is game between all the team, and then you can just wonder, okay, what are the different divisions here? So if you use community graph plot, in a second you can actually detect the community and see the divisions in your graph, in your social network. So this is actually one of the aspects and application of community detections. So now let's go to the network level. So now I will just talk about assortativity, mixing, as well as homophily. Homophily, which is the tendency of people of the same characteristic to connect together. So in this example, I have a social network of friendship in a high school. So you can ask, how people in that high school are connected together. So if you use graph assortativity, you get a positive number, a number. So usually the assortativity mixing gives you a number between -1 and 1. And when that number is positive, that means people with that same characteristic tend to connect together. So this value just tell you that popular kid in high school connect to popular kid in high school. So highly social, you connect to people which are highly social. So, and now, besides just looking at it, can you can ask a question like, from this network, can you figure out if people from, with the same race are connected together? So you can do that in one line. You do graph assortativity, and then you just put as second argument race, and then you compute it. So this is still a positive number, which tell you that people of the same race connect together, but it's kind of slightly smaller than the previous value. So higher, popular kids tend to connect with more popular kids. Race is slightly lower. So this is kind of a glimpse of what we have, in version 9. There is several more functionality as clustering, statistical analysis. I will not present here, but feel free to ask me questions later on. But before I close, I will first, try to give you a set of pointers where you can actually go and get more information about our functionality. So we have our documentation, which is both in product and online. So you can click on, look at the social network guide pages, which kind of give you the structure and the general idea of how people do social network analysis, as well as the functionality, including also some other feature, I'm not talking about here, which is, statistical analysis, an aspect of that. And you have also graph and network. So if you're, in the pure theoretical side and you want to actually see the graphs which actually represent your network and, play with it, you can actually do that. And also there is, quite interesting example in our guide page, in our marketing page, where you can actually go and look at those examples. So for example here, this is a short study of the social media /dot, which have a community. You can import the data, look at some statistical information about it, and study the degree distribution and see how people connect there and exchange information. So these are a good set of examples to actually show you how the functionality is available. Zach, that's pretty much it.
Yeah, no, there's some great examples there, and a few follow-up questions for you. Do we plan on supporting other social media sites?
Yes. So has the demand come and how we found people found how those if some of those sites are really interesting, we'll be happy to actually provide those sites. As I said before, our social media data is a parklet, so we can actually push it live in a couple of the new sites and such a thing. So, if you have favorite website, social sites, so feel free to let us know. And,
Yeah, we're always wanting to hear feedback. So if there's a site that we don't currently support and you want us to look into it, give us the feedback. We would love to hear what our Mathematica users would love to try out our data on as well. One more question, a very important question for many users. Are personal Facebook data and passwords stored in Mathematica?
No. So essentially, we don't store any data, and it's just per session. So that means the data you download or you have in Mathematica reside on that session and reside in memory. So if you quit Mathematica, the data is gone. So we don't store anything. We have no information.
Fantastic. And like Charles said, if you want to learn more about the social media data and about the social network analysis, head to the Documentation Center or head to wolfram.com/mathematica. Another presentation all ready to go. Let's head over to Andy here. And Andy, survival and reliability analysis, brand new in Mathematica 9.
Yeah, kind of a totally different topic from the social network analysis, but survival and reliability, nonetheless, very important topic. And I want to share with you some of the new things that we have in version 9 for that. So let's look first at survival analysis. Well, what is it? Survival analysis is it's modeling of time to event data. And oftentimes that event is something very dire, like death in biological organisms or failure in a mechanical system, but it doesn't have to be something dire like that. It could be the time to your first employment after going to college, for example. So oftentimes that event that we're interested in, the exact time that it happens isn't exactly known to us. So we might only know that the event happens on some interval. In that case, we would have what's called censoring. Or we might only be aware of individuals over some particular interval. And in that case, we have what's called truncation. So there's this special data for survival analysis, and we need ways to handle that. Just to give you kind of a graphical representation of censoring, what I'm talking about, we have a matrix plot here. The squares represent events where we know exactly what time that event happened. So like in this case, this event happened at time 10, say 10 weeks. But then we also have events here that are called right-censored. Notice that they're open on the right-hand side. This means that there's a lower bound, in this case 11, at which that event could have occurred, but then we don't know exactly when it happened. So maybe this is someone was on a study and we were following them until their death and they didn't die by the end of the study, so we don't know when that might be. So we're going to look at some new tools for survival analysis in Mathematica 9. And I'm going to go over a couple of practical examples, time to failure for cooling fans, and survival of patients with cancer of the larynx. So first, the new tools for working with survival analysis. Now, I don't have time to go over everything that's there, so this is just sort of a brief overview. But some of the really key concepts are how do we actually get this censored and truncated data into Mathematica in the first place? What kinds of models can we fit with it? And then what kinds of special hypothesis testing functions are available for working with survival data. So to get our data into the system, we have a function called event data. And this is effectively a wrapper that lets us work with censored and truncated data, just like it's any other data in Mathematica. So here's an example where I have two arguments being fed to event data. The first argument are the event times. So let's just say that these are measured in weeks. This second one could be 23 weeks, for example. The second argument to event data here is a list of censoring indicators. In Mathematica, a 0 indicates that the individual died or the unit failed or something like that, and a 1 indicates right censoring. It didn't fail by the end of the study. So once I enter that into the system, I can work with it just like any other data. So I can compute descriptive statistics with it. For example, here's a 5-number summary computed with quantile just directly on that event data. I compute a probability. What's the probability someone survives longer than 22 weeks, say? Or here is an expectation, which is actually a mean residual life computation, saying what's the expected lifetime beyond 22 given I survive at least that long. So another 2 weeks, 2 years, whatever. So we can compute these descriptive statistics and probabilities right out of the box, but we can also fit models with this pretty directly. So estimated distribution is something that we introduced in version 8 that allows us to estimate parameters for all of our many parametric distributions. We can do this with event data just fine. So here we have a Weibull distribution, which is very commonly used in survival analysis, and I get a maximum likelihood estimate out. We can also do non-parametric estimates. So here's a kernel density estimator. I have a bandwidth parameter h. I'm leaving that symbolic. And the reason for that is so that I can let this bandwidth or smoothing parameter vary. What I'm seeing in this manipulate is the non-parametric kernel density estimate of the survival function. Notice it's a step function right now that looks something like a Kaplan-Meier estimator, for those of you who are familiar with that. And I have my parametric Weibull estimate of the survival curve. Now, I can let this bandwidth vary, and what that does is, as it gets larger, I'm smoothing out my non-parametric estimate. So as it smooths out, it starts to look more like the parametric estimator. So that's great. We can do all of these things just right out of the box with event data. But in survival analysis, there are a lot of more interesting and advanced kinds of analysis you might want to do. For example, you might want to have confidence intervals about some of these survival probabilities. You may want to perform some kind of regression and get diagnostics and residuals and these sorts of things. So we've added in 9 survival model fit and Cox model fit to do just these things. So here is a survival model fit of my event data that I've been working with. And what this allows me to do, it's kind of like linear model fit that we've had around for a while. It lets me query all sorts of properties once I've fit the model. So this manipulate here, I'm hiding the code. I just have a survival model fit, and I'm extracting point-wise bands and an event table, and then plotting the survival curve. So let's look at what that does. Got the survival curve, the point-wise confidence intervals about those survival probabilities, and here's the event table that came out. I've actually linked this up so that we can vary the confidence interval, or the confidence level, and as that confidence level gets large, the intervals get larger as well. So Cox model fit and survival model fit have a number of hypothesis tests sort of built into them as properties, but there are other kinds of tests that we might want to do that maybe fit sort of outside of that range. So we have this function log rank test that is built in to be able to compare hazard rates and survival functions for different groups of event data. So here I have a couple of event data objects. Enter those into the system. I can see visually that the survival functions look different, but that's not a statistical measure. I might be interested in saying, okay, well, is that difference statistically significant? Well, that's where log rank test comes in. So here I'm going to perform a log rank test and produce a test data table. At the 5% level, I would say that there's a significant difference in the hazard rates for these two populations. Okay, so that's a taste of the new kinds of stuff that's there. Let's look at some applied examples for how to actually use it. So this first example is time to failure for cooling fans, and these are computer cooling fans. So say I have a collection of 70 such fans that I've selected for testing, and at the end of the study, 12 of those fans have failed. That means 58 of them are still around and still functioning. Well, I don't want to just throw that information away, so this is where the survival analysis and handling censored data comes in. These are write censored data. And that data is just stored in my event data object here, and I'm estimating an exponential distribution for those fan lifetimes. And the plot that comes out here using survival model fit against the exponential looks like the non-parametric and parametric estimators agree reasonably well. Once I've fit this model, in this case I'm using the exponential distribution, I can compute all sorts of things from that. So this is the median time to failure for fans, about 17,000 hours. And this is the probability that a fan lasts longer than 8,000 hours. It's about 0.72. So here's more of a sort of clinical example. survival of patients with cancer of the larynx. This is a famous data set in survival analysis. We have 90 male patients, and they were diagnosed with cancer of the larynx at a certain age, and they are each in one of 4 stages of cancer, with stage 1 being the least severe and stage 4 being the most severe. Kind of hiding the data from you, but this function Cox model fit, which is an extension of survival model fit to allow for other explanatory variables, I'm going to use that to create a model here. So notice that I have these variables stage and age. That's actually what's coded up in my covariates. Stage of cancer, age at entry to study. Serve here is the actual event times, the censored data. So I have nominal variables goes to stage. The reason for that is because stage is actually not something I would want to treat as numeric. It's a categorical response. So this allows me to treat it as a categorical variable. Let me make sure that I have that entered. Once I've done that, this model that comes out works very much like a linear model fit. I can extract all sorts of properties. One that I think is really interesting and important is this parameter table. It has lots of good information stored in it. So the parameter estimates themselves, something about how significant those parameter estimates are. And the column that I find most interesting is this relative risk column. So with a Cox model, we're always comparing to some baseline. In this case, we're comparing everything to those with stage 1 cancer. So what this is showing, so for example, this parameter estimate is highly significant. The relative risk for stage 4 is 4.44, or 5.44, which means people with stage 4 cancer are 5.44 times as likely to die as those with stage 1. So it's much better to be in stage 1 than stage 4. Now, unlike a lot of other software packages, we actually have made it possible to easily visualize the survival curves from our Cox models. So here what I'm doing is showing the survival curves for the 4 different stages of cancer, and I'm allowing the age at which the individuals entered the study to vary. So coming in at an early age and being in a low stage of cancer is the best prognosis. If I come in at a later age and I'm in a higher stage of cancer, that's bad news. And we can see that this is all acting pretty quickly and smoothly. All right, so that's it for survival analysis. Now I want to talk about a related topic, reliability analysis. Reliability deals with independent components that are connected into a bigger system. Well, we're interested in, we know something about the survival of those individual components, and we call that the reliability of the component. So reliability of a component is the probability that that component's functioning at a given time. Reliability analysis allows us to take these components with these known distributions, connect them together, and say something about how long the system itself is going to survive. So here's just a diagram to give you an idea of what I mean. Say we have a process that we want to get through from start to end. We have 3 components in this case, and in order to make a path from start to end, D1 has to function, and either D2 or D3 do. So I'm going to talk about some new tools in Mathematica 9 for doing this, and I'm going to show a couple of application examples, reliability of computer processors and the reliability of a car. So these new tools that I'm going to cover, and this is by no means all of what's there. There's a lot more, and I'll point you to a link later. I'm going to talk about some models that are very powerful, reliability distribution and standby distribution. So let's start first with reliability distribution. So given that we know the reliability distributions of the components, and we know something about how they're connected together, we can use reliability distribution to say something about the survival of the entire system. So here's that same picture that I showed before with the 3 components, where D1 has to function and either D2 or D3 do in order to get to the end. We code that up in reliability distribution as such, D1 and D2 or D3. And I see that I'm giving component distributions for each of the components. So these are all exponential, and they have various lambda parameters. So this is all symbolic. I expect my mean time to failure to also be symbolic. And I can compute the survival function, or in this domain, we would call it the reliability function. Another model that's new to 9 is standby distribution. So sometimes you have a component that is either really likely to fail, so what comes to mind would be fuses, or you have a component that if it fails, it's just catastrophic. So I think of O-rings in a space shuttle, for example. So what we do in those circumstances is try to build up a bunch of backups that are redundant, that'll kick on when one of them fails. So that's what standby distribution allows us to model. These backup components are activated when one of them fails, and here what we're going to see is a cold standby system with imperfect switching. So standby distribution lets us work with cold and warm standby. Cold standby means that the component doesn't start to decay or until it's actually been activated, whereas warm standby means that it's actually decaying as soon as the whole system's activated. Imperfect switching, what this P parameter means, it's the probability that I effectively switch over from one component to the other when one of those components fails. If I had perfect switching, it's just going to switch right over and have no trouble with a probability of 1. So here, I'm going to look at the mean. Again, it's going to be symbolic, and the survival or reliability function. The cool thing is that standby distribution can actually be used as a component in a reliability distribution. So extending that picture I showed a little bit before, we still have D1, D2, D3, but now I'm allowing for backups for D1. So now as long as any one of these D1s kicks in and works, I'll make it to the choice of D2 or D3. And this manipulate is showing what the reliability function looks like for this system if I have different numbers of backups. If I don't have any backups, the reliability is low, and as I increase the number of backups, the reliability of the entire system increases. So an application example, we're going to look back at the fans that I was talking about in the scope of computer processors. So suppose that a computer processor has 2 cooling fans, and one of those fans has to operate to keep the processor from overheating. So we're going to bring back that data on the cooling fans that I had with the survival analysis part and get that estimated exponential distribution. And I'm going to use those that I've estimated from event data, and I have to say at least one of them has to work in order for this system to not fail. So the median survival of the fan itself is about 17,000 hours, as we saw before, but now that we have 2 of them, we have 30,000 hours median survival for the whole system. And because this is a distribution, we can do things like simulate it. So here I'm going to simulate processor lifetimes until they overheat, 10,000 of them. It's pretty much instantaneous. Okay, the reliability analysis of a car. So this is a very simple model for a car. The idea is that if I start at my starting destination, or starting point, and I need to get somewhere safely, there are several things that have to work. My wheels have to work, my engine, my transmission, and one of my 2 brake systems. All modern cars have 2 brake systems. So we code this up in a reliability distribution saying the wheels and the engine and the transmission and one of the brake systems have to work for me to get safely where I'm going. Now this is all symbolic, but let's add some numbers to get a sort of realistic model. This is the mean time to failure. I'm using expectations in expectation here with those parameter values plugged in. This is how long I expect a car to last, assuming I had to perform 0 maintenance on it. So about 3 years with no maintenance. And hopefully it's not the brakes that fail. So now let's do, since this is a distribution, why don't we just simulate some time to failure for 100 cars. The horizontal line here is showing the mean time to failure. We see that many of them are above that and many of them are below it. So I didn't have time to cover very much information here at all, but there's a whole lot of information out there online for you to access. One good place to look is at our new and 9 pages. This one for survival analysis has a lot of the, not only examples that I showed here, but a host of other ones, and gives some taste of the kinds of things that you can do. We also have one for reliability, and then we have guide pages, which give a rundown of the different kinds of functions that we have in Mathematica for this particular domain. And you see that reliability covers a whole lot more than just the 2 pieces that I introduced here. That's about all I have, Zach.
Well, Andy, I guess one question that I have for you right away is, you mentioned the right censoring examples. What sorts of other censoring and truncation can you work with inside Mathematica 9?
That's a good question. Okay, well, we can actually work with a whole range of, I talked about censoring being an interval. Right censoring can actually be specified as an interval from some time t to infinity. We can be fully general about that. We can say left censoring from minus infinity to some time t, or we can say interval censoring from t1 to t2. We can do the same level of generality with truncation, and we can mix and match those things any way we want. And actually, if we look at the documentation for event data, there's plenty of information on how to get all these different kinds of censoring into the object. Let's look, pardon the scrolling. Yes, specifying censoring and truncation. So each and every kind of censoring and truncation that's handled by event data is documented there in what I would consider very simple examples to show how to get just that kind of censoring into the system.
A lot of the examples that you've shown here have used small data sets. How well does this scale to much larger data sets?
Well, let's see. So yeah, I agree. We use the small data sets because they're kind of cleaner and easier to look at, but I can just try to create something here. Let's just say that I had data as random variate from, say, an exponential distribution and do, I don't know, 100,000 of them. And I'll say that my censoring indicators are a random choice, 0, 1, so I'm going to have right censoring, and I want 10 to the 5th of those. So now let's do a survival model fit of my event data sends. Takes a little bit, but it's done. And now let's do a plot of that survival function where t goes from 0 to 25. And we'll say exclusions goes to none. Pretty rapid. So it scales relatively well.
It looks like it did scale pretty well. Well, if you want to know more about that or find some examples, head to the Documentation Center. You can also learn more at wolfram.com/Mathematica. One more presentation and we'll hand things over to Roger here. And Roger, tell us about another new feature inside Mathematica 9, random processes.
All right, thank you. So I'll give you an introduction or an overview to random processes in Mathematica 9. So random processes is the major new feature for probability and statistics. You've already seen a few. This is one that we've spent a lot of effort on. Some of the big classes of processes that we will eventually talk about include Markov processes, queuing processes. We've all been in queues. Time series, which many of you probably are familiar with, stochastic differential equations. All of these have sort of a wide variety of things, and these are some of the examples that you can find on the marketing pages, and there's many additional applications in the documentation. We'll cover some of these, but most of it you will find on those pages. So the first part of this talk, I'm going to try to give you a little bit of a framework, a way to think about this, and then we're going to dig into these other classes of processes. So first of all, a random process is the analog of a dynamic system when you think of deterministic things. So things like differential equations, difference equations, and so on, these are things that we've had in Mathematica for a long time. Now, if we allow randomness to also sneak into the system, then you don't just have one path, you have many possible paths that the system can generate. So one aspect of that is that we can have things that have various classifications like this, that the time, either there's sort of a discrete set of times like the integers, like a sequence, or continuous time, that for any time that the process has a value, but also the actual value can be both continuous and discrete. So let's go and look at that, a few examples. So those of you who are familiar with distributions will recognize the framework that we've set up. So each process, it has a name that ends in process. The few simple processes just have a few parameters. If I want to simulate a process, I need to indicate over how long, what amount of time. If I do that, I'll get something back that's called temporal data. This is something that's independently useful for dealing with time series data, such as you might get from all kinds of places. Now let's just look at the plot of that, and here we can see what that process actually looks like. So pause on process is a sort of a simple process. It kind of models traffic flow, for instance. So this one will count from 0, and then it will just sort of add an integer increment every time some event happens. Every time a car passes, it will count up. So this one has discrete state, but it has continuous time. At every point in time, you have an actual count. Now, you can also generate many of these simulations. So even if you generate many of them, it will store it in temporal data. And if we plot those, you can see that we have many possible sort of traffic scenarios. So here is, standing out by the road 10 different times counting cars, if you like. And this is how your count would have varied by time. Now, just as for distributions, we can generate data. So this one will generate data. It will allow you to sort of simulate something that goes on and see how it's going to behave. We can also use data that we use from measurements and so on and figure out which model is the best of all possible models in a class to describe that data. So let me generate some synthetic artificial data here by simulating. And now I can take that data as input, and I can indicate which family of random processes do I want to consider. So here I say I want to consider the Poisson processes, but I keep the parameter as a symbolic thing, and it will find the best of all possible parameters that fit that. In this case, it's a maximum likelihood fit. This is not very good because I don't have that much data. If I extended the data either longer in time or more copies, I would get more data. So if let's do the 10 times counting cars, and now when I fit it, you can see it's getting closer. And the more data you get, the closer, the better your approximation or your estimation will be. That's kind of a big topic in itself, but we've made it just as simple as estimation for distributions. Now, here's an overview of all the processes that we provide with Mathematica 9, and there's about 30 of them. This group here with continuous state, these are often known as time series processes. Well, that's what they're known as. These guys here are stochastic differential equation type processes, and we played with just one, which is a Poisson process. And all these discrete state ones, they're typically finite state or infinite state kinds of processes. Another concept that's useful to understand as the backdrop. And all the things I mentioned now, they apply to all processes, regardless of which one. So these are universal kinds of things. Now, if I look at the process at a certain time t, and so we see here along this axis I have time t, and along here I have the state value. If I look at any one of those slices, and let's do it, instead of looking at that, I'm going to go back to that graph, but let's say that I run some simulations that you saw me do. I can put I can slice my data. I can put a cut in my data and see here the red dots are all the places where my path crosses that line. If I use those as data points and I estimate a density function from that, like the smooth histogram function in Mathematica, then the bubbly curve here is what that density function looks like. The dashed one is the theoretical one. But you can see as I move my slice around, I get sort of a different density. What this means that every time I slice through here, I get a distribution. And we can see the PDF of that distribution to the left. And that's exactly what these pictures above here was trying to show. For every point in time, if I go out in the x direction, I can see what the PDF looks like. So here is a slice, for what that PDF looks like. And the same for all these cases. Now, the way you indicate that in Mathematica, so we looked at Poisson process. I can slice by just applying it to t, because it's kind of like applying a function at some point in time. And for some processes, particularly the simpler ones, we can compute that distribution in closed form. So here you can see that there's in fact a Poisson distribution, but the parameter for that Poisson distribution is going to vary by time. Some other simple processes like a Wiener process, you can see that the single slice distribution is just a normal, and you can see how the mean changes, it drifts linearly, and how the standard deviation also changes. Now, we can do the plot that I was hinting at above, we can look at all of these PDFs. So here is time, and here's my state x. And so for each time here, I get some PDF. Okay, so here I'm plotting this infinitely many at the same time. Another way to think about these things is as a marginal distribution. If you think of a multivariate distribution, this is computing in marginal, except there are infinitely many of them. So that's a slight complication. Now, the fact that you get a distribution out or a random variable out when you slice means that you have a ways to connect it, and connect it to random variables and distributions, and everything that you expect to work does work. So these are perfectly good random variables. So here's a Poisson distribution. I've sliced it at 1, and now I can use that to simulate, to generate random numbers. I can compute probabilities. So if I slice it at some point t, I can find out what's the probability that the value is less than 5 at that point in time for the process. Now, I kept a lot of things symbolic here, the parameter, the time, and so on. So the answer also includes symbolic parameters. Here's an example of using that. So let's assume that the price of some financial asset is modeled by this process, the Wiener process. And you can make this much more complicated. Now, what I'm interested in so this is a financial option, let's say, and the financial option is worth, I'm betting on the fact that the price is going to be greater than 12, let's say $12. So if the price at some time t, when this option matures, is greater than 12, I get the profit. If it's less than 12, I get nothing. So the way to say that is max of this and 0. So how much profit can I expect? Given that this varies randomly, what's my expected profit? Well, you just formulate it exactly, the way you expect. It's an expectation. And in this case, I kept many things symbolic, so you get something, how it depends on parameters that you add in your process, which allows you to, for instance, see how sensitive it is with respect to many of these parameters. Now, so slice of a process is a distribution. That means that everything we can do for distribution just works. Now, for random processes, many of these things have names. So for instance, if I compute the mean of that distribution, that's called the mean function for random processes. If I compute the median, that's the median function, and a whole slew of other things. The way you call that in Mathematica is just what you see here. Instead of introducing new functions called mean functions and so on, you just apply mean to the sliced process. So here's the mean, median, standard deviation functions, and this is for the Wiener process, and we can see that mean and median grows linearly, and the standard deviation grows like a square root with respect to if this was finance, we would call this volatility, but the standard deviation. Okay. We can also compare that from the data side, which we did when we first introduced it here. So let's use a process, let's simulate it, and now I can compute the mean for every point in time for that collection of data. So I have, in this case, I simulate 100 paths from a Wiener process, and I compute the mean by slicing through at every point in time. And this bubbly curve here is what I estimate from data. The dashed one is the theoretical ones. Now, this idea of slices, I can generalize to take more than one slice. So if I put up another bar here, I make a bivariate slice, and I can keep on going. In fact, this is the thing of defining all slice distribution is an equivalent way of defining every process according to the structure theorem by Kolmogorov. So it's not only sort of cool to do, it's actually the very general definition of a random process. Okay, so we'll see some more practical uses of these. You saw some now, but now we move into the second part of the talk, which sort of dives into some groups of these processes and how you specify them and kinds of things that you might be interested in analyzing. First group is finite Markov processes. And one way to think about them is basically as random walks on a graph. They're finite, so they're a finite number of states. You specify transition probabilities between the states. So here is one way, this is how you can specify a discrete Markov process. You start in the state 3, and then you specify the probability of transitioning from, in the first row, This is the probability of transitioning to state 1 again, to state 2, and then there's zero probability to state 3 and 4, and so on. So this is called the transition probability matrix. If I do that, I can actually convert that to a graph and look what it looks like. So here I don't put the probabilities, except they are there as tooltips. So we talked about 1, so there's a 0.5%, there's 0.5 probability of going back to 1 again, and there's 0.5 probability to go to state 2. But I can't go to 3 or 4, and we see that by those zeros there. Now, let's simulate this process, a number of times. So I simulated 15 times, and what we can see, if we look at all these, that pretty much either I seem to get stuck in either 1 or 2 and oscillate between them, or I get stuck in 4. If I do it one more time, we should have similar kinds of behavior. Now I get stuck in 4 more often, and we could have figured that out by just looking at the graph, obviously. So there's no way to return to 3. So either I go to either 1 or 2, in which case I can oscillate between them. That's the only thing that can happen. Or I go to 4 and I'm stuck in 4. So that's exactly what we would have guessed from the graph. Now, I can do various analytic kinds of computations too. So if I say that x is from, in this process, now a different way to slice is to sort of indicate the time that I'm slicing in the variable itself. So what's the probability that at time 10 I'm in state 1? That probability is a third. Or over long periods of time, what fraction of time do I expect to be in state 1? If I do many scenarios here. Again, a third. Now, something that we do for many of these classes is that we provide additional service functions that effectively produce a report. And everything that you see here in this table you can individually call and compute with. But this sort of basic report sort of summarizes a lot of it. So you can see things like initial probability, transition matrix, and some of the structural things that I hinted at. So for instance, one thing that you can see which are the sort of communicating classes. Communicating classes of states are things where you can go from one to the other. So for instance, if we look over here in the actual graph, we can kind of see that I can go between 1 and 2, but I can never go to anything else. I can't go from these guys to either 3 or 4. When I'm in 4, I can just be stuck in 4, and so on. So that's what those classes are, and they have big impact on when you want to understand the long-term behavior of one of these Markov chains. Often they're big ones that we study. Okay. Now, another way to define a graph is to just define a Markov process is just to start with a graph, and then we can use, instead of using a matrix there, I just use a graph, and now that's a discrete Markov process, and we can look at it, convert it back to a graph, and we can see that this actually comes from how a knight would move on a chessboard, and I pick a really small chessboard here, just a 4x4. But you can see where they go, and if I hover over them, I can see what the probabilities are. It will pick uniform probability for everything that's reachable out from each node. Okay, let's use that and just simulate it. Here's the simulation. I can sort of run around. You can see this is the state I'm in. This is where I came from. And this is just what I choose because it was kind of confusing to just see the state. And so I'm jumping around like a random, a knight picking random possible moves. If I do that on a slightly bigger chessboard, like a 25 by 25 chessboard, run a simulation, this is basically a random move on a chessboard for a knight. So absolutely any graph, and we already saw, and that graph could be a social network, for instance, It could be, these are my friends, and what's the probability of me getting in touch with such and such through, a rumor getting started somewhere. What's the chance of that, what's the probability of that reaching, so and so. All right, another important class of random processes are queues. Well, we've all been in queues at airports or stores and so on. The mathematical model of a queue is fairly simple. It has an actual queue as we think of a queue. It has a process or a server, In this case, it has one server, but you can also have, for one queue, you can have multiple servers, 3 in this case. In some cases, we can also limit the size, how many we allow to be in a queue. If too many people, if someone tried to enter a queue when it's already full, it will be rejected. So for instance, some real technical systems behave this way. When you lift your phone and try to get a dial tone, if the system is overloaded, it will just reject you. This whole theory was developed in order to be able to understand things like packet switching, which is something that led to Ethernet and subsequently Internet. So all of these are stochastic systems, and the question is, what kind of capacity can you get out of a Ethernet, for instance? It's not clear that will scale well. But also in modern times, it's used to analyze service, like a call center and things like that. So let's just get a little bit more understanding how this model works. The state of a queue, of a queuing process, is the number of jobs or customers in the system. So here I have a single queue and a single server. The service rate, you give two numbers here, which is the service rate mu and the arrival rate lambda. And this means really that the exponential distribution between the arrivals, or exponential distribution between the service finished. Now, if so mu is the service rate. If I have more people arriving, so I up the arrival rate, what we see is that we start to get more bubbles, right? We get more, the length of queues goes up, and the closer that I get, the more these bubbles will go up. If I actually pass, so I have more people arriving than can get serviced, they arrive faster than I can service them, I will eventually have a blow up. So here's an example where I blew up beyond my sort of plot range here. So that's something that you might be interested in dimensioning your system to be able to provide decent queue lengths or wait times. Those two are in fact some of the most important things that people are interested in for queues. What's the expected? So we again, like we did for Markov processes, we have service functions that give you summary tables. So one of the most important performance measures is system size, which is everybody in the system, whether in the queue or being at the server, or queue length, which is people in the queue. Or what's the expected time to run through the system and get out on the other side. Now, these things, vary, of course, as you generalize. If I have more servers, I get different results. If I have sort of limitations, I get different results. But these are all the things that you kind of would have guessed, probably. Another variant of queues is that we connect them together, like in another network. So for instance, if you go to an airport, you go to one queue, you go to check-in, you go to security, then you go to boarding and so on. This happens in technical systems too, like web servers are usually forking off jobs to each other. And so the question is, how does this whole system behave? I won't go into that now, but you'll find examples in the notebook and on our marketing page. Next group of interesting processes are time series processes. Mathematically speaking, a time series process is just a set of difference equations that are driven by white Gaussian noise. You have something that varies with no temporal dependence, that just as input to these difference equations. Practically, you use this as black box models to model things where you don't necessarily have a very good model. So things like unemployment rate or exchange rates or various finance kinds of things. Now, so here is a really simple process. So this is what it means. This is a first order difference equation. And what comes in here is just basically white noise, meaning that it's not dependent on each other in time. Okay, so here's my process. I can compute everything you saw me compute. The mean function is 0. Here's the covariance function. I can compute the slice distribution, which are all, Gaussian here because I drive it with Gaussian. But one important thing that people often are interested in is to look at covariance function or dependence in time. Now, these guys, for processes, they can generally have all kinds of shapes. They're always symmetric. But you see these particular ones for time series, they look exactly the same outside of the diagonal, regardless of where I'm on the diagonal. So around here, it looks the same as around here. That's known as weak stationarity. So people often look at just that particular direction. You look at the covariance function along the anti-diagonal. And so these are pictures that you might recognize. Now, this, often you can tell a lot by looking at this about the process. How far in time do things affect each other? So for instance, in this case, I can see that only 2 steps in time can the process affect each other. And if I'm farther out, they're really unaffected. Whereas for this AR process, they affect each other all the way out. Less and less, but they keep on affecting each other. Now, so let's use this to model some data. So I'm going to read in some weather data. Here's the temperature in Champagne. Let's look at it. This is what it looks like. Weather has this particular feature that probably 24 hours later, it's not going to be unrelated to what it was today. So it has sort of this seasonal or cyclic behavior. You know, there's a special class of time series processes that are called, you know, usually has an S in their name for seasonal. So seasonal ARMA process. And I'm going to say that the cycle here is 24. We can also detect that and so on with tests. But let's do this. Let's estimate our process from that. What's going on? I think I've mistakenly defined B. Okay, so there we have estimated the process. Now I can use that process to forecast what the future weather might be like. So let's say I want to forecast it 3 days in advance, so 3 times 24. And now I get, again, a temporal data object. Let's display them together. So here's the measured weather, here's the predicted or forecasted weather. Many more things to say about time series, but let's get on to the final group of random processes. These are stochastic differential equations. They're very similar to time series, except instead of using difference equations, we use differential equations. But again, we drive them with white Gaussian noise. Okay, so let's do a really simple example. So this is basically x prime equals to minus x. But then I want to sort of send in white Gaussian, white noise to perturb it a little bit. So let's simulate that. So I can specify that in a notation, which is very much what you would expect, the classical notation for it. So here's my differential equation, a stochastic differential equation. So let's just look at the first case where I have no noise in. And then we get, as we expect, this sort of deterministic solution, e to the minus t. Now let's then as we add more and more noise in, we can see that gets folded in to the solution. In the beginning, we can't affect it very much, but over time, it sort of compounds itself. And then when I really up the noise level, I get something that's pretty wild. So that's simulation. Now, if I define one of these processes, again, everything works just as I described it. I can compute the mean function, various functions. We can use those two to sort of bound simulations. So here's my simulation. I'm plotting the mean functions plus minus 3 standard deviation, and I expect about 99 or 99% of it to be within these bounds. We can also compute other things like slice distribution. In this case, here's the PDF for the slice distribution, and we can look at it. Here with x and t, and we can see that how it sort of follows the mean function, but it gets sort of wider and wider because the noise sort of compounds, and I have less and less localized solution. Many special processes are, in fact, of this kind. So Wiener process we've been using a lot, which is integrated white noise, is one of these. Ito processes, geometric Brownian motion, and many more. These can be automatically converted into this form to get it there. There's much more to say about stochastic differential equations than all of these processes. But when you want to learn more, so first of all, there's a nice group of marketing pages that's on the What's New site for Mathematica. Here's random processes. You're going to recognize some of the pictures from my talk. And there are similar ones for Markov queuing processes and so on. But also, built into the system, guide page that describes more clearly, the scope of the project and so on. And there are separate guide pages for all of the things that we discussed here, and those are also available on the web. That concludes my talk, and I'm sorry, apologize for this. It's a blinding fast presentation, but at least I hope that it gave you some taste of it.
Thank you. You certainly covered some great examples there, and there were some examples that we skipped over, but you can download that notebook soon, and you can look at everything that we did not talk about and everything that we did. I do have a quick follow-up question from a viewer. Do you offer priority queues?
We do not. We do offer general queues in the sense that you can have the queues that I showed are called MM1 queues or MM queues, which means that there are exponential times between arrivals, there is exponential time between services finished. You can generalize that to use absolutely any distribution. So those are usually called MG, GM, GG, and so on. We're planning to extend to offer more kinds of queue disciplines. So we also allow for limited queue, but more kinds of queue disciplines include priority queues that you mentioned, but also bulk arrivals. It's another kind that we hope to add in the future. Okay, great. And like Roger said, head to the Documentation Center for more information about sample code, and you can find out when you can learn about the random processes, and you can check out his notebook as well. Of course, you can learn more at wolfram.com/Mathematica.